Hello, welcome to the lecture for Wednesday, August 29th, and this will make up for me not being in class. I am starting out with the schedule just like normal, and I've started, you'll notice, adding topics to the different days so you can keep track of what we've covered on what day. So Monday we started into Chapter 2 material, so that's contingency tables. We covered some of our terminology, we talked about difference between two proportions, we talked about relative risk, and then we left off right before the last measure of association, which was the odds ratio. So I'll start there today. And I'll also talk about some R coding, and then I'll finish off today's lecture with two different tests of independence. Don't forget you've got your homework due, so I've got that posted for the 29th, and as long as you get it to me by Monday morning at 9. And homework 2 again is posted and complete, so you can get started on that. I am out for the 29th, but if you have questions, feel free to email me. We have a holiday on Monday, so no class there. But again, I'll be on email, so if you have questions, just shoot me an email. And looking ahead, you should be thinking about ideas for projects, and if you want to also send ideas to me, I'm happy to kind of go back and forth with you on that. So that's our schedule. And with that, let's take a look. So we are to our third strategy for association testing. Right, so we're with our 2x2 tables, and we are interested in looking at whether two different variables are associated. So we talked about how one measure is looking at difference in proportions, and another measure is relative risk, and made the point that if you're looking at something that has a very small probability, how those two measures can be very different. So that was one of the major distinctions between how relative risk can be, in some situations, a lot more drastic and perhaps more meaningful than looking at a difference in proportions. And so after that, our third measure then is the odds ratio. And so odds, so if you're someone who gambles, you might be familiar with odds, but we'll go through and define it in terms of our symbols. So we've got our pi still, so our probability of response. And so your odds are defined to be that probability, so probability of your, say, success divided by probability of failure. And so if you've got one group, so here I've got odds sub I, so I can calculate the odds for the ith group. So if I wanted to compare, so the odds ratio is then to take the odds for two groups and compare them by taking the ratio of them. Not surprisingly, if we want to estimate those, and we're going to take our estimated probabilities and substitute those in for pi, right? So not a big surprise. So our odds ratio is defined to be the odds for one group divided by the odds for the other group. And here, if there is no difference between your two groups, then you're going to have an odds ratio of 1. So we're going to be interested in looking at tests of whether our odds ratio is equal to 1. One nice thing that you'll see is when you're estimating the odds ratio, and another term actually for what the odds ratio is called is it's also called the cross product ratio. So if you substitute in your sample sizes and your sizes for your different cells, your cell counts, and you simplify that down, you'll notice that it actually comes down to, on the top, you've got the multiplication of the diagonal divided by then the multiplication of the off diagonal. And so the odds ratio you'll see sometimes is called the cross product ratio. Right? So same thing, but getting at what the actual form of the estimate looks like. One thing to just point out, and you can actually see that here especially, is that the order of whether you've conditioned on rows or you've conditioned on columns isn't going to matter, right? So you've got the diagonal, regardless of how you've reordered rows and columns, the odds ratio is always going to come out to be the same. So that's kind of a nice thing to keep in mind. So as with the relative risk, our sampling distribution for your odds ratio can be skewed. And so we're again going to work on confidence intervals based on the log of the odds ratio. And so we're going to have our standard error. So it's our asymptotic standard error. So we're going to be okay with using this if we have a large enough sample. And so here is the square root of the sum of the inverse of all of the sample sizes. And we'll use the same process then for coming up with a confidence interval for the odds ratio as we did with our relative risk. And we'll go through that with our example. So let's take a look and grab your pencil. And if you remember, let's flip back and look at our count data. Make sure we remember what that table looked like. Here we go. So we had our 14 and our 21 on the diagonals, and then we had 9 and 1 on the off diagonal. So 14, yes, yes, and then we had 21 that were the no group, right? So in terms of estimating your odds ratio, it's actually going to be 14 times 21 divided by 9 times 1. So that'll give you your estimated odds ratio. All right, so let's write this out, and you'll have to bear with me typing this within Word. It'll be a little bit clunky, but a head start right there. So we've got our estimated odds ratio. I've got the diagonal product on the top, off diagonal product on the bottom, and if you put that into your calculator, it comes out to be, let's round that up, so 32.67. So we want to do our confidence interval, and so we're actually going to have to do the log odds. Right, so I'm going to want the log odds, and that is estimated. So the log odds, and I'm using R to get my answers, so I've got the log of 32.67. And so that comes out to be around 3.49. All right, so log odds is 3.49. We also need our standard error. So we've got, our standard error for our log odds. Alright, and that, boy, that's a pain, equals, so we need to take the square root and we are going to sum up 1 over 14, so we need to take the sum of the inverse of our counts. So 1 over 14, 1 over 21, 1 over 1, and 1 over 9. Alright, and then let's see what that is equal to. So let's go over in R. So I've got the square root of 1 over 14 plus 1 over 9 plus 1 over 1 plus 1 over 21. So those are all of my counts. So I get a 1.109. So that would give me my standard error. And then after that, I would need my, so I've got my log odds, I've got my standard error. So we can pick our favorite 95%. So the 95% confidence interval for the log odds, right? So for our parameter is going to be, right? So we have our estimate 3.49, and that's going to be plus and minus. So the 1.96 is our critical value, and then times our 1.109 for our standard error. All right, so let's go do that. So we have 3.48, or was that 3.49? 3.49, that is our estimate. Okay, so 3.49 minus my critical value of 1.96 times 1.109, that will give me my lower bound. So my lower bound is going to be 1.3. Could round it up if you want at that point. I use the up arrow to get back to what I had typed. I'm going to change that to a plus. So I've got my 3.49 plus my critical value times my standard error, which gives me my upper, which is 5.66-ish. And so there is my confidence interval for the log odds ratio. Right, so we're not really interested in the confidence interval for the log odds ratio. It's just a means to an end. What we really want is the 95% confidence interval for our odds ratio. Right, so what we need to do is take E to our lower and our upper bound. So this is going to be E. So I'm going to just copy this down here. Right, so we need to take each of those and put them into the exponential function. And let's see what that equals. So our lower gives us a value of 3.73, and our upper gives us a value of something very large. So 3.73 for our lower, and for our upper I have 288.2. 288.20. Right. So that is my 95% confidence interval for my odds ratio. And then at this point you can ask, so is your odds ratio significantly different from 1? Right, so 1 would be your test of whether there's an association or not between your two variables. And again, since we can look within our interval and see that the odds for one group, and so this would be the odds for the group that, so the odds of healing for the group that's had thalidomide is between 4 to 300 times greater than the group that had placebo. Right, so that doesn't include 1. It's also fairly significant even at the lower bound. Right, we have 4 times as much healing. And so the answer is yes, since the confidence interval does not contain 1. Right. So it's nice in that we see the consistency between each of those measures. So all of them end up with a significant result showing that the two are associated. Depending on whether you're more comfortable talking about relative risks, odds ratios, or differences in proportions, the interpretation can be a little bit different. All right, so that gets you your testing. Now I went ahead and put the script up in R, but I wanted to kind of step through and have a look at that. And since the data here is small, I just entered it. So I entered it, I have quotes here, so by hand, as opposed to reading in a data set. And if you're brand new to R, again, I'm encouraging you to come in. If there are any commands you're not familiar with, you can always take a look at help. So if you're curious about what matrix does, you can type help matrix, and that will open up help for you so you can read about what the different options are for the matrix function. So what I've done here at the top, so I set up a matrix. So let's step through this. So the first line defines a matrix C. All right, it defines it to have 2 rows and 2 columns, and I'm populating it by row, and the data that I'm using is 14, 9, 1, 21. So by row it goes 14, 9, and then it goes to the next row 1 and 21. Right, so that's our table. The next thing is just so the next row is just to make it a little more user-friendly. So I gave the dimensions names and I put labels on them. right? So now when I print C out, you'll see that it looks a little bit nicer in terms of actually being a table that you can recognize. And I then forced it into to be a table, right? So as opposed to being a mathematical matrix, now C is, it looks the same, but by creating it such that it's technically a table object in R, there are a few nice functions that we can use on the table. So getting things like adding margins, getting proportions from tables, getting marginal tables. So we'll go through a few of those. And these are all things that you could go through and just manually sum up yourself. But if you're dealing with contingency tables and you're going to be doing it a good amount, there's some nice functions to know. So this next chunk, so I'm interested in, let's see, so the first thing I'm going to do is get my marginal tables. Right, so let's just run the first one and see what happens. Right, so notice that it's called margin.table. I gave it my table, and then I said margin equal to 1. Okay, so the margin 1 is the row, margin 2 is the column. And so what it's done is gone through and it created our marginal row, our marginal sums. So for our row, yes, it went across and it said there were 14 plus 9, so 23 said yes. And for no, 1 plus 21, so there were 22 that said no. Right, so that, with big tables would save you some work. So if I change that margin to 2, so it's the next line. And again, feel free to pause this, to check out the help functions, and to kind of play with this as you're watching the video. So margin equals 2 then gives us, for the columns, it sums up the number of yeses and it sums up the number of nos. So that would be nice if you're just looking for that information. If you are wanting to keep your table but add the margins around the sides, the function add margins will do that for you. So you'll notice here's my 2 by 2 table, and then on the outside you've got the row sums, the column sums, and then the total sample size in that corner. All right, so that'll save you some work. That'll give you your numbers you need for finding your proportions. And then if you want to be really lazy and not have to do the proportions yourself, you can construct it using this prop.table. So again, row has a margin of 1 and column has a margin of 2. So when I said prop.table C margin equals 1, so let's see what it does. So if you look within the row, it's going to go through and standardize and create a proportion table. So you'll notice that 0.6-ish, 0.4, this adds to 1. So it's creating the conditional distribution by rows. So for those that used thalidomide, 60% had healing. For those that did not, around 4% had healing. Right, so that's what prop.table will do for you. And then if I change the margin to 2, then it's conditioning on the column. So for the column being yes, it's going to go through and say, right, so we've got counts of 14 and 1. So this top one is going to be 14 out of 15, and the bottom one will be 1 out of 15. Right, so you can see that's where that came from. So it'll help you get to some of your conditional probabilities. So those would be just summary measures. In terms of our tests, so if you wanted to go through and do a proportions test, so a comparison of two proportions, then the function prop.test will do that for you. And this question mark prop test will get you to help. It's the same as typing help and in parentheses putting prop.test. So it tells you what your options are. So if you want to do that, you can read a little bit more about the function. And I am asking it to do a proportion test, and I'm giving it my table, my C table. And let's see, what else have I told you here? So the confidence interval is your walled interval. The score, the test is actually the score test. And if you take a look on, let's see, so slide 47 is where we had gone through and done so we had done a confidence interval. And so our confidence interval was, let's see, between 0.346 and 0.781. So that was our walled interval. And that is from right here. And the score test is done by a test of equality. And let's see, we actually, to do the score test, we haven't gone through this, but if you've looked at comparing two proportions in other coursework, this does a pooled estimate for your proportion and uses that to come up with its standard error. And so I show you down here in terms of the calculation how it came up with that. Right, so I'll let you play with that on your own. All right, relative risk. So as best I know, there isn't a built-in function, so I actually just programmed it up. And this is something that if you wanted to, take the code and kind of play with it, some of you, if you want to get really fancy, you could make your own function for it, and just all that's changing is your P1 and P2 and your N1 and N2, and then your formulas stay the same because you've got your standard error, your lower and your upper, your relative risk, and then the confidence interval bounds for the relative risk. Oh, and then of course you'd also want to change your critical value option there. But if I run through all of that, that will confirm what we did on slide 50, or at least it better. So on slide 50, we had a confidence interval of 1.92 to 93.44. So that'll match with our previous work. Same thing with the odds ratio. So I went through and estimated it. Again, there's not something that's automatically built in, but we came up with these bounds and this particular odds ratio. So you can use that code to play around with alternative data sets. All right, so it'll give you some R coding. So in terms of the results for our case study, right, so something to think about. So would you say the results suggest that thalidomide is more effective at healing mouse ulcers than the placebo? And as a result of these trials, researchers actually suspended the current trial and started giving thalidomide to all of the patients. And so then the question would be, do you agree with that decision? And so I'll let you guys think about your what you think about that, and maybe we can discuss it when we are back together in class. Okay, so one thing to think about is the relationship between the odds ratio and the relative risk. So take a second, pause, and think about in words how you would describe relative risk and how you would describe the odds ratio. Right, trusting that you did that. So in words, okay, if I had to think about what the relative risk tells me. So the relative risk, so it tells you how much more or less likely you are to have success, so whatever you're focusing on, given x equals 1 compared to x equals 2. Let's see if that makes sense. So relative risk tells you how much more or less likely you are to have success given x equals 1 than x equals 2. Right, so if that's disease, perhaps you're comparing disease in men compared to disease in women. And at least to me, and I think oftentimes when you listen to studies reported, relative risk is often used. It's often an intuitive way to compare disease risk. Now, odds ratio is similar, but it tells you how much higher or lower your odds of success are. So how much higher or lower your odds of success are. Again, given x equals 1, so given one level of your explanatory variable versus x equals 2. And I don't know about you, but I don't think in terms of odds. I think a little bit more in terms of probabilities and proportions. So, they're very different interpretations. And a lot of times, even though you might have the odds ratio, you'll often see people misinterpret it, so that's something to look for, right? If you're given an odds ratio, you are comparing odds. You're not comparing two probabilities, so you should be conscientious of that. And I do think that if you can estimate both, that oftentimes just the general public will find it a lot easier to understand the relative risk rather than the odds ratio. Okay, fortunately, there's actually a nice relationship that exists between the two. So let's walk through what I've got here. So what I'm starting out with is just writing out the formula for the odds ratio. So on the top I've got the odds for x equal to 1, so for one level of your row variable or your explanatory variable. And then on the bottom I've got the odds for the other level. And then from here to here, just did some rearranging. And then from here to here, one of the things you'll notice is that out in the front, you actually have the relative risk. So relative risk is your probability of success in one group divided by that probability in the second group. So there's your relative risk. And then you're left with this ratio of the failure probabilities. So your odds ratio is equal to your relative risk times this multiplication factor. And what often happens is we're dealing with things where the probability of your quote success, so whatever you're focusing on, often is low. And if that is the case, take a look at what's going to happen to this term, right? If pi 1 and pi 2 are smallish, then this ratio is going to be approximately 1. And then what happens is your odds ratio is going to be approximately equal to your relative risk, right? So when those probabilities are small, so your odds ratio is approximately equal to the relative risk. And it turns out there's going to be a scenario where this is going to be a very good thing. Right? So let's take a look at an example to see such a scenario. All right, so we have a 20-year study of British male physicians, and they noted that the proportion who died from lung cancer was 0.0014 per year for cigarette smokers versus 0.0001 per year for non-smokers. Right, so we're in that scenario. We're focusing on something, right? So quote our success. Okay, not really a success, but what our focus is on cancer. And what we're conditioning on as terms of x equals 1 versus x equals 2 is smoking versus not. And then they also looked at the proportion who died from heart disease, and that was 0.00669 for smokers and 0.00413 for non-smokers. So what I thought would be a good exercise to do is to compute your relative risk and your odds ratio for describing the association between lung cancer and the association with heart disease. So it'll give us a good practice on estimating these. Also, let's go ahead and throw in the difference in proportions so we can compare all three of those measures. And then once you've got those calculated, let's look at what we think about what's more strongly associated with the two, with smoking. So go ahead and pause, take a few minutes, go through and calculate that. So calculate all three measures of association. Calculate that for comparing smoking with lung cancer and smoking with heart disease, and then come back to the video to check your answer. Alright, I hope you're back to check your answers. So when I went through my calculations, I, for lung cancer, got a relative risk of 14 and an odds ratio estimate of 14.02. Notice those are close to each other, and that's as we would expect since the probability of your quote success, so the outcome that we were interested in, is really small. So we'd expect those to be close together. For our heart disease, same thing. So in the relative risk I estimated to be 1.62, the odds ratio to be 1.624, and again those are very close to each other, and that is expected since we're dealing with probability of our quote success being again small. Looking at your relative risk and your odds ratio, it's clear that lung cancer is much more associated with smoking than heart disease. Right? So your relative risk, your probability of dying from lung cancer, given that you smoke, is 14 times higher than if you did not smoke. Right? So that's a nice interpretation, and generally, again, I think it's easier to interpret that from the relative risk perspective. Otherwise, you can say that your odds of dying from lung cancer are 14 times that if you smoked compared to if you did not smoke. And for heart disease, you got that's compared to 1.6 times. Right? So lung cancer has a much stronger association. Now, if you were to look at the difference in proportions, that's not as obvious. Right, so the difference in the probabilities for lung cancer is 0.0013, which is actually smaller than if you looked at the difference for heart disease. Right, so again, if you're dealing with small probabilities, your relative risk is going to be potentially a better interpretation. This is especially true when you're translating this to large populations, which is often the case when you're looking at disease studies. Right, so that gives you one example. All right. So, one last question I think I had for you guys. So another reason why the relationship between the relative risk and the odds ratio is useful is that there are a lot of studies that are done that are retrospective. So these would be our case control studies, would be a major example as a retrospective study design. And we're interested in, so we've collected a certain number of cases, a certain number of controls, and then we are measuring something, and we're interested in whether or not there is an association between that explanatory variable and our disease. And in this particular example, I've got, let's see, so this was from the text, so table 2.4, and they were looking at patients that had had a heart attack, so a myocardial infarction. And they had sampled for each patient that had had an MI, they had taken 2 control patients. So it's a 1 case to 2 control design. And then for those individuals, they'd asked them if they had smoked or not. So a couple of questions from this data. So can you estimate the probability of an MI? So the probability of a heart attack. Can you estimate relative risk? And can you estimate the odds ratio? So give it a second, pause, think about what you can actually estimate from these data. So thinking about the first question, okay, so no, you can't, right? If you wanted to truly estimate the probability of a heart attack, you'd have to take a sample of the population and look at what proportion of that sample had suffered from a heart attack. Here we have fixed the design. We're taking 1 person that has had an MI and 2 people that have not. Right? So if we try to do an estimate, right, then our estimate is going to be 1 out of 3 people have had a heart attack. Okay, clearly that's not correct. That's just how our design was taken. So no, we cannot. Let's make that a little larger for you. So no, so samples are drawn. So you have MI cases with 2 controls per case. Okay, so that means you can't estimate the probability of an MI. Okay, so you can estimate the probability of smoking given case status. Okay, so that's something you can estimate. So the design would allow for that. Okay, Perhaps we're not interested in that though. I mean, we would be able to look at smoking, we could think about the relative risk of smoking, and we could condition on MI. All right, so since you can estimate the probability of smoking, you can estimate and look at the relative risk of smoking, and this would be done by conditioning on MI status. And we're not really interested in that, right? So it's not really of interest. And this is where the comparability of the relative risk and the odds ratio come in. So regardless of the fact that we have done a design that has restricted the number of cases and the number of controls, we can actually estimate the odds ratio. And when I introduced the odds ratio, I pointed out that it actually didn't matter whether we had rows or columns and in what order, right? So conditioning on rows will give you the exact same value as conditioning on columns, right? So that equivalence will allow us to estimate the odds ratio even in this particular scenario. So we can't estimate the relative risk of MI conditioning on smoking. Okay, so that's what we're really interested in, but we can't do that. We can estimate the odds ratio, right? And so if I wanted to look at that, where's my table? So take my cross product concept. So 172 times 346 divided by 90 times 173. Right, so my OR estimate is going to be equal to 172 times 346 divided by 90 times 173. Okay, so I've got my numerator, I've got my denominator. Let's look at what that equals. Right, that equals 3.82. So that equals 3.82. Right, so that tells us that your odds of an MI are 3.82 times higher if you've smoked than if you've not smoked. Right? Okay, so how can we translate that? So if the rate of MI in smokers and non-smokers is low, and we'd expect in the general population it's not incredibly high, so it's low, then the OR is going to be approximately the same as the relative risk. And you'll actually see this happen a lot. So you'll see a case control study where they've estimated the odds ratio, and then oftentimes they'll interpret it in terms of the relative risk. And well, that's not completely correct. As long as they're dealing with something that has a small probability, the interpretation will still hold up. So that's something to just be conscious of. And that's a great thing for case control studies, especially. All right, I think actually we should probably stop there. I think we've gone for long enough. So I will pick up on Wednesday with the chi-square test of independence, and we will start off there. So have a great break, and I will see you in class Wednesday.